We know that mountains are hotspots of climate change, and when we say mountains, there are many that have glaciers still, like the Himalayas, Alps. Of course, Andes is losing a lot of the glaciers now, and Venezuela may be seeing the disappearance of its glacier, and so on. This nice review paper talks about elevation dependent climate change in the mountain environments. I'm going to make a brief summary of it. It's a very nice long article with lots of details and incredible list of references that you want to follow up with. I want to capture just a few main processes that they are summarizing. Mountain regions show rapid environmental changes under anthropogenic warming. The rates of these changes are often stratified by elevation. This is obvious in the Himalaya as well. And Himalaya is complicated also because it's stretched east-west, so the east has got a slightly different set of climate change impacts happening, the center to the west, and so on. The impact of Pacific and Indian Ocean changes, El Nino and so on, to Indian Ocean dipole, and the western disturbances on the west and so on are all adding. I'm mentioning Himalaya because I'm mostly interested in that, because I'm sitting in India as I'm doing this. The rates of these changes are often stratified by elevation, leading to elevation dependent climate change, or EDCC, elevation dependent climate change. In this review, we examine evidence of systematic change in the elevation profiles of air temperature and precipitation, including snow. Many places are seeing more cloud bursts, more hailstorms, and many of the mountains are also home to orchards like apples, or they have other fruits and vineyards and so on. On a global scale, differences between mountain and lowland trends for temperature, precipitation, and snowfall are 0.21 degrees C per century. That's enhanced mountain warming, and minus 11.5 mm per century with enhanced mountain drying, snowfall droughts, and minus 25.6 mm per century of enhanced mountain snow loss, respectively. So it's actually a retreat of the snow line. This is for 1980 to 2020, based on averaging available gridded data sets, typically coming from reanalysis. Reanalysis products have all kinds of issues in resolving mountains, but nonetheless, this is the best we got. Regional analyses sometimes show opposite trend patterns. So people take the global reanalysis and do regional reanalysis. People have done it for many of the mountain ranges. This EDCC is primarily driven by changes in surface albedo, specific humidity, and atmospheric aerosol concentrations. So solar dimming versus other indirect effects, and also ice albedo, snow albedo feedbacks. Throughout the 21st century, most models predict that enhanced warming in mountain regions will continue at 0.13 degree per century on average, but precipitation changes are less certain. Models always have trouble doing precipitation, and it's hard to do because we've discussed this elsewhere. Temperatures have nice large decorrelation scales and more direct response to anthropogenic forcing, whereas precipitation tends to be much more complicated, especially when you have mountain ranges with lots of little valleys and peaks. You have microscale circulations that are hardly resolved by models or data. Superimposed upon these global trends, EDCC patterns can vary substantially between mountain regions. Patterns in the Rockies and the Tibetan Plateau are more consistent with the global mean than other regions. So Rockies are way over there in North America, and Tibetan Plateau is here in the Asian region. In situ mountain observations are skewed towards low elevations, and understanding the EDCC is biased towards mid-latitudes, where people have collected more data. Efforts to address this uneven data distribution and to increase the spatial and temporal resolution of models of mountain processes are urgently needed to understand the impacts of EDCC on ecological and hydrological systems. Many of the glaciers feed a lot of the rivers on which millions, if not billions, of people depend, and they are often hotspots for geopolitical conflicts as well, in terms of sharing waters and so on, even sharing the glaciers. Just a brief bit of the introduction. Although global mean air temperatures has increased by about 1.1 degrees C since the pre-industrial levels, obviously this is now at about 1.3 or 1.4, the rates of the anthropogenic warming are highly spatially heterogeneous. Arctic regions in particular have experienced warming, so that's polar amplification or Arctic amplification. As elevated and mountainous regions share many thermal characteristics with polar regions, they too tend to show warming rates higher than global average, albeit with complexity related to topographically driven microclimates that I mentioned. Such positive elevation dependent warming, EDW, elevation dependent warming, is evident at historical and longer timescales, and despite much variation according to time of day, season, and location, the mean warming at high elevation is 50% faster than the global mean since the 1950s, basically based on reanalysis data. However, elevation dependence is not restricted to temperature. Broader elevation dependent climate change, EDCC, is becoming apparent, as we'll see in a minute, encompassing atmospheric moisture content, precipitation, snow cover, and surface albedo, radiation and energy balances, and wind regimes as well. Indeed, gridded data sets demonstrate systematic changes in precipitation and snowfall trends with elevation. Okay. Here are the key processes. You can see they are numbered. You have wildfires, you have snow line radiation and winds, so long wave, short wave, anabatic winds, katabatic winds, climbing side, sinking side, or descending side, tree lines along with snow lines, and so on. So factors and processes associated with elevation dependent climate change in mountain environments. Here is a schematic figure of the processes associated with, resulting from, or contributing to elevation dependent climate changes. Where changes are dominantly in one direction, these are indicated by plus and minus for positive and negative changes, respectively. They are not feedbacks, they are just changes going in the positive or negative direction. So, reduced snowfall, for example, or increasing temperatures, and so on. One here start with the winds, prevailing winds. Upper level prevailing winds interact with the mountains. Prevailing winds create windward and leeward effects of with differential gradients. And two is obviously here is two change in cloud base height and moisture with associated heavy precipitation and changes in cloud forest elevation. You can imagine that the summer warming can increase humidity and maybe snowfall, whereas winter warming may change snowfall into rain, and this is happening a lot in many places. Thirdly, changes in cloud properties and specific humidity, which reduce incoming solar flux but increase downward long wave flux. So here you have that process, radiative process, is happening with interaction of long wave with clouds and short wave interacting with albedos. You can see the interactions here on snowy peaks and dark surfaces, albedo effects. For strengthening upslope anabatic winds and weakening downslope katabatic winds. So strong anabatic winds, weak katabatic winds. So a lot of the cloud bursts and hailstorms often are related to warm airs rushing into the slopes and more moisture coming in, sometimes non-local. In the Himalayas, you have moisture fluxes from the Arabian Sea now feeding more and more of the northwestern Himalayan slopes, for example. Increasing stream flow extremes and variability. I always look at these when I'm reading and then I forget. 4 is here. You can see that 6 goes here and 7 goes there and 8 is here. So I have to find 5 is here, way down here. We should remember because it's saying stream flow extremes and variability. 6 is glacier retreat influencing downstream fluvial regimes and habitats. That is this part here, upstream of 5. 7, increase in snowline elevation and changes in snowpack above snowline. So that's up here. 8, snow albedo decrease. We just pointed to 8 here, negative. So you can follow it. This is up, so snow lines are going up. Precipitation, and 2, for example, was change in cloud base height and moisture with associated heavy precipitation and changes in cloud forest in elevation, which is positive as well. I'm getting a mosquito bite here, unfortunately. Okay, strengthening upslope, but 8 was snow albedo decrease. 9, migration and possible expansion or contraction of vegetation zone slopes here. Also seeing some precipitation, and landslides are a big challenge as well in places where there has been heavy construction or heavy rainfall events, which is very typical now in Himalayan foothills. 10, anthropogenic aerosol declines, but wildfire aerosol increases. So wildfires are shown here, and you can see here decline in anthropogenic aerosols, but wildfire aerosols are adding here positive numbers. 11, high elevation plateau creates mass elevation effect and reduces the influence of free air processes. That's up here. And 12, changing frequencies of temperature inversion formation and cold air pools in mountain alleys and local mesoscale circulations that we mentioned. 13, permafrost degradation leading to mass wasting. That's down here. And many of the processes tend to amplify mountain change rather than subdue it. There are not too many negative feedbacks in that sense. Jumping ahead, the discussion on all these processes, I'm skipping. Expected vertical profiles of important mountain variables in a warmer world. You can see elevation, and this is the change of temperature with time dt. So the trend is increasing and with elevation. So here you are looking at precipitation trend, which has an increase. Sorry, here is a negative number and here are positive numbers. So you have the lifting condensation level at present, which is getting lifted, as we mentioned, at about the cloud base properties here, and the future lifting condensation level is here, and you can see the change in precipitation rate is very much elevation dependent, even though temperature is not showing such a great elevation dependence. That is more than just that is not other than anything but linear. Whereas albedo, again, you have current tree line, future tree line. Tree lines affect snow cover greatly, and you have above the tree line you have snow lines, so current snow line and future snow line. The best estimate of the current change in air temperature T over time of temperature T with time and elevation and warming, you can see that's a complex sentence. The best estimate of the rate of change in air temperature T over time T with elevation and warming. The profile represents the global mean. The regional profiles could differ owing to local processes, not drawn to scale. Here, of course, the schematic. As in B, B is as in panel A, but for precipitation, and C is for albedo, and different variables show markedly different profiles. Lifting condensation level, LCL. Obviously, these are very schematic, and global means over the mountains may not have much meaning. Nonetheless, this is how we have done things to understand elevation dependent warming. You tend to average and look for processes that make sense together. Expected elevational profiles of changes in other variables in a warmer world. Although height dependence of temperature, precipitation, and albedo changes with warming are well examined, other important variables are less so. These include specific humidity, surface winds, aerosols, and solar radiation. Specific humidity, then, with warming, specific humidity Q is theorized to increase at all elevations. So we are going to look at associated with this, you're going to see a specific humidity which is going to come up here. So dq dt, you can see that with elevation yeah obviously it is low at high elevation and high at low elevation. So we have to see the curve this way. I suddenly got stumped by it. Right, so dq dt, rate of change in Q with time. However, assuming a constant temperature increase with height, absolute increases in Q will be greater at low elevation, as we saw the curve just a minute ago. This difference emerges because of higher temperatures at lower elevation that non-linearly increase the moisture holding capacity, Clausius-Clapeyron, of the atmosphere. At changes in Q will have larger relative effect at higher elevations owing to the lower initial Q, with implications for cloud formation and other processes. Patterns in Q will be modified regionally by global scale climate dynamics, leading to spatial variations in moisture. We'll see some global maps where this will become clearer. Surface winds. Changes are also expected in surface winds U, including an intensification of daytime upslope winds and a weakening of nighttime downslope winds, anabatic and katabatic, that we mentioned before. These changes are theorized to be largely driven by shifts in snow lines and tree lines. During the day, rising snow lines lead to uncovered bare rocky ground at higher elevations, driving surface heating that switches downslope katabatic winds over snow to upslope anabatic winds over rocks, so albedo effects and heating effects. As maximum surface temperature change between rock and snow occurs under solar heating during the day, the strongest wind changes will occur during this time. Around the tree line, the replacement of bare rock with forest and corresponding effects on evaporative fluxes, surface roughness, and albedo, etc., will have the net effect of decreasing upslope wind speeds. Thus, daytime upslope winds will increase at high elevations from snow line changes, but decrease at lower elevations from tree line changes in a trend sense. So there is a trend in snow line and tree line, and that affects the diurnal cycle of anabatic and katabatic winds. Right, so chronic and acute changes interacting with each other. Different changes, acute changes in general are extremes and anomalies at weather time scale, whereas here we are just talking about diurnal cycles affected by background state changes. Different changes emerge at night when the switch from snow to rock at higher elevations decreases radiative cooling at the surface, weakening nocturnal downslope winds. Likewise, the combination of increased roughness and reduced long-wave radiation efficiency, so lower sky view factor, reduces surface cooling, weakening downslope flow below the new tree line. Accordingly, nighttime downslope winds will weaken at all elevations. Sorry, I keep looking for the mosquito. Anthropogenic aerosols, then, we said they are decreasing in many places. Anthropogenic aerosols such as black carbon and sulfates are theorized to decline in the future at elevations. So panel C will see AOD, aerosol optical depth. A reduction in aerosols is expected at all elevations due to a combination of more stringent air pollution control policies and technological advances. So we have now jumped into projections. So tree line, snow line changes are also future climate. So we are not really separating what's already happening and what is expected to happen with future projections, continued warming, unfortunately. However, the decline will be relatively larger at low elevations because of the greater initial concentrations associated with proximity to popular centers and the short lifespan. This reduction ignores any changes in thermal circulations and any strengthening of upslope winds, as we'll see, which could transfer a larger proportion of the remaining aerosols upslope, even if not a large absolute amount than at present. So radiation, on the other hand, incoming solar radiation as at the mountain surface is theorized to decline in the future, as Q is the first order driver of solar radiation reaching the surface via impacts on cloud optical depth. Q is humidity. Its increase with rising temperatures lead to a proportional and inverse decrease in S at the mountain surface. The largest decrease will occur at low elevations where the atmospheric column is the deepest. Any change will depend on relative rates of cloud optical thickness change at different altitudes, given that the majority of aerosols scatter radiation, and absorption and scattering of light by aerosols is influenced by uptake of water. The strength of the effect of Q will be modified by the concentration of aerosols throughout the atmosphere, so it's a bit complicated. Changes in other radiation components are also important. Reflected solar radiation will be strongly related to any changes in surface albedo. Of course, outgoing long wave will primarily depend on surface temperature, which is expected to increase more at high elevations. Downwelling long wave radiation has a nonlinear dependence on Q and is expected to increase more rapidly at higher elevations. Downwelling Q, which will have an impact on snow lines in turn. Okay, trends in mountain low. So let's look at the figure first. So as we said, Q initially is low at high elevation, colder temperatures, and high at lower elevations. But you can see this is how dq dt and elevation are related. So dq dt is obviously Q is going to increase with elevation. This figure makes it very confusing, but nonetheless the winds, tree line and snow line dependence again, with nighttime downslope impacts and daytime upslope impacts based on albedo and heating effects and surface roughness, albedo and tree line effects. So you can see the decrease here and increase and decrease. This is aerosols, so aerosol optical depth at low elevations and high elevations. In the future they are expected to decrease because of climate action, which is a projection. Solar radiation, you can see again elevation dependence, where humidity effects are going to determine the penetration to the surface. The main point I want to make here in terms of trends in mountain, lowland differences in temperature, precipitation and snowfall, they're looking at different data sets: global, Andes, Himalayan mountains and Tibetan plateau, and for 1960 to 2020 and 1980 to 2020. You can see that the trends depend very much on the product you use, and the differences are not small. So here you are going from 0.06 in CRU to GISTM GPCC at 0.15, so almost 2.5 times, and Berkeley is similar, but at a 5 is 0.22, that's almost 4 times as high as CRU. Precipitation changes also very different, -3 in GPCC, but -28 in millimeter per year per century. Millimeter per year is the precipitation, per century is the trend. So that's the main point I would leave you with, that we have unfortunately very sparse and very different data, especially for precipitation. Even though they are often dealing with the same data sources, they somehow process them and come up with gridded products. Remember, this analysis is using gridded products, not in situ local instrumental data. When gridding happens, all kinds of processing and massaging happens, so temperature differences tend to be smaller than precipitation differences, which is unfortunate. But even in the models, temperatures tend to be closer to reality than precipitation. But precipitation data itself is problematic, so how do you know how wrong the models are? Well, these are big problems. Nonetheless, the rates for 1980 to 2020 are larger for all of them, temperature, precipitation and snow, because the global warming and elevation dependent climate change and elevation dependent warming are all accelerating with time as we get closer to the recent period. So global here, so let's look at the I probably have to split this into two podcasts because this will be too long. This is already 25 minutes. So let me stop here, then we'll come back and look at observed temperature and precipitation changes in mountain regions. So there is the historical period, and then there is the projection part that we already mentioned in terms of expected aerosol, humidity, snowfall, snow line, tree line changes, and so on. Okay, so I'm being very brief. The paper is nice, as I said. Please follow up on your own if this topic is of interest to you. Okay, we'll come back and finish the rest of the paper. Okay.